Alright guys, this is day 8. Alright, we're going to be looking at pages 6 through 10 in your textbook. So if you want to go ahead and get that open, I'm going to refer to your textbook quite a bit. Let's go ahead. Like I said, this is a lot of stuff that you should already know. But let's look at the basic properties of algebra. It says algebra involves the use of letters and other symbols to represent real numbers. A variable is a letter or symbol. For example, the two common ones that we see is X and Y. But you can use just about any type of letter or symbol that represents an unspecified real number. A constant is a letter or symbol, for example, -2, 0, square root of 3, pi, that represents a number. A specific real number. An algebraic expression is a combination of variables and constants involving addition, subtraction, multiplication, division, powers, and more. Roots. So, guys, going back to your very beginning algebra days, skip down and look at the subtraction. We can rewrite a subtraction sentence as an addition sentence. Remember, subtraction and negatives are interchangeable. So we can rewrite a subtraction sentence as an addition sentence with a negative number. So A minus B can be rewritten as A plus a negative B. We can rewrite a division sentence, A over B, or A divided by B can also be the same thing as A times 1 over B, where B cannot equal 0. Alright? Additive inverse, if you remember, additive inverse means to be the opposite. So if I'm looking at B, then negative B would be the opposite. And 1 over B is the multiplicative inverse, or what we call the reciprocal. We deal with reciprocals a lot in geometry, so hopefully you remember that word. One thing you need to remember is additive inverses are not always negative. The additive inverse of 5 is a negative number, -5. But the additive inverse of -3 would be +3. So additive inverses are opposites. Multiplicative inverses are reciprocals. All right, we're going to get into the next green box. Guys, these are your properties. Commutative property, associative property, identity property, inverse property, distributive property. These are 5 properties that are not new to you or should not be new to you. We have used these. You should have used these probably all the way down into middle school. All right, associative property. If you remember, associative property looks like this. If I have 1 plus 8, then I can say that's the same thing as 8 plus 1. All right, that's my commutative property. If 8 plus 1 is the same thing as 1 plus 8. Multiplication, because you do have the commutative property of addition, the commutative property of multiplication. So 8 times 1 is the same thing as saying 1 times 8. You were taught when you started adding and multiplying that it did not matter what order you did your numbers in. That is because of the commutative property. Then we have the associative property. The associative property of addition is just basically how we group numbers together. Alright, so let's say that I have 4 plus 5 plus 5. Let's say I want to make that a little bit easier to add. So the associative property tells me that I can do this. That instead of adding 4 plus 5 first, that I could add 5 plus 5 first. 5 plus 5 is 10 plus 4 is 14. It's a little easier than 4 plus 5 is 9, 9 plus 5 is 14. Yes, this is a simple problem, but the associative property makes some of our more difficult problems a little easier. It's the same thing with multiplication. let's say that I have 9 times 3 times 5. Let's say instead of saying, okay, 27 times 5, let's say I want to look at it like this. Let's say I want to multiply 3 times 5 first, and then multiply 15 times 9. It's a preference, but the associative property allows me to group whatever I want to do first. Identity property, when you have the identity property of addition, the identity property of addition basically, think about identity. When you are trying to identify something, you're trying to identify yourself. You're trying to identify what that thing is. All right, so think about a number. If I want to know what can I do to a number that would give me itself, all right, well, if I want to have an identity property, let's say I want to know the identity property of 5. When it comes to addition, I would add 0 to 5, and it does not change. All right? So 5 plus 0 gives me the exact same thing. Let's say that I want to do multiplication. Well, what times a number gives me the exact same number? I multiply times 1, and that gives me the exact same number. So the identity property is taking a number, and what can I do to that number to give me the same number? The inverse property tells me this. Let's say that I have 5. What can I add to 5 that would give me 0? Well, guys, remember, inverse is opposite. All right? The additive inverse is opposite. So when I add additive inverses, I'm always going to get 0. Let's think about what happens when I do the inverse property with multiplication. All right? If you go back, the multiplicative inverse or reciprocal would be this. So 5 times 1/5 actually gives me 5 over 5, which is 1. So on the inverse property, when I add inverses, I get 0. But when I multiply inverses, I get 1. The distributive property, guys, hopefully by now you've used distributive property enough that you know how to use it. Distributive property just tells me that I have to distribute whatever is outside the parentheses inside the parentheses. So if I have 5 on the outside of parentheses and I have 1 plus x on the inside of parentheses, I have to multiply that 5 times everything. So 5 plus 5x. Okay? That is my distributive property. The left-handed sides of the equations for the distributive property show the factored form of the algebraic expressions, and the right-handed side shows the expanded form. All right, so back to the problem we just did. This is the factored form. All right, this is our factored form. And this is the expanded form. All right? So using the distributive property, it says write the expanded form of a plus 2 times x. Well, in order to do that, guys, I'm using distributive property. Tells me that I need to distribute x among everything that is inside that parentheses. So a times x is ax, and 2 times x is 2x. So this would be our expanded form of that expression. B is a little bit different. It says write the factored form of 3y minus by. Well, at this point in time, I've got to figure out what they have in common. In order to figure that out, in order to figure out how to write that factored form, I need something they have in common. So look at this, 3y minus by. There's no number they have in common. One's a 3 and one's a b. So, but they do have a y in common. So I can pull a y out. And when I pull that y out of 3y, I have 3 left. And when I pull a y out of negative by, I have negative b left. So this would be my factored form of 3y minus by. Look for what they have in common. Alright, next green box. Here are some properties of the additive inverse together with examples that help illustrate their meanings. So, if I have u and v are real numbers, variables are algebraic expressions. If I have a negative, if it looks like this, negative times a negative number, guys, that is the same thing as saying negative 1. Alright, that is the exact same thing as saying negative 1. So if I say negative 1 times negative u, well, negative times a negative is a positive, and 1 times u is u. Alright? So take a few minutes and kind of look through those properties. We're not going to spend a whole lot of time on them because we have a lot to do. Alright, go to page 8. Exponential notation is used to show products of factors that repeat. For example, negative 30 times negative 30 times negative 30 times negative 3 is the same thing as negative 3 to the 4th power. Alright? And 2x plus 1 times 2x plus 1 is the same thing as 2x plus 1 squared. Make sure you remember how to write that. Alright, so exponential notation, let a be real numbers, variables are algebraic expressions, and n a positive integer. So you can write it like this. Alright, so a to the n would be a times a times a times a, whatever n stands for. So if I have a to the 5th power, then that's the same thing as saying a times a times a times a times a. This is going to be n factors. However many it tells you here on that exponent. N's the exponent, a is my base, and a to the n is the nth power of a. Alright. 2 exponential expressions in example 6 have the same value, but have different bases. Be sure you understand the difference. Alright? So let's look at A. So I have the natural log of negative 3 to the 5th power. The base is negative 3. Okay? Now, let's talk about this and why. I want you to look at these two examples. What's the difference between the two? Alright? You'll notice that this one has parentheses. This one does not. Alright. Now, that parentheses is extremely important. The reason I say that is because if the negative sign is inside the parentheses, that means that the base is negative 3. on this one, the base is not -3 because the negative part is not being done 5 times. In this case, it would be 3 to the 5th power, and then everything would be negative. All right? So the base here is 3. 3 is the only thing that's being multiplied 5 times, not -3. So if it's inside the parentheses, that's part of your base. So in this case, it would be -3 times -3 times -3 times -3 times -3. Here, it's going to be negative, and then 3 times 3 times 3 times 3 times 3. Okay? They have the same value, but you need to make sure you understand the difference between the bases. All right? Take a few minutes to look at those properties of exponents. Make sure you remember, if I have a power times a power, then I add the actual powers if they have the same bases. All right? Division of same base powers, I would subtract my exponents. If I have a power raised to 0, if I have a base raised to 0 power, I'm always going to get 1. All right? If I have a base to a negative exponent, then I can rewrite that as a fraction. If I am raising something, look at the 5th one, UV is in parentheses, and I'm raising that to the nth power. That means everything inside that parentheses is being raised to the nth power. Okay? So U to the M, V to the M. If I'm raising a power to a power, then I multiply those powers. And if I am looking at number 7, U over V, and that is all raised to the nth power, that means U is raised to the nth, V is raised to the nth. Like I said, guys, this is a lot of review. All right, so looking at example number 7, it says simplify expressions involving powers. All right, the first time you look at that, you're probably going, oh my gosh, that's absolutely crazy. But it really isn't. All right, so I have 2ab to the 3rd. And then I have 5a squared b to the 5th. All right, now, the one thing you want to make sure you remember is you've got to look at things that have like bases. So let's look at this. So the 2 and the 5 are alike. Then I have A's. Then I have B's. So if you go back and you look at this, this is just like property number 1. All right. So what I'm going to do is I am going to go ahead and multiply that 2 times that 5, and it gives me 10. Then I'm going to look at my A's. This is property number 1. When I am multiplying like bases, then I add my exponents. So I have 1a here and I have 2a's here. So 1 plus 2 is 3. When I have b to the 3rd and b to the 5th, so 3 plus 5 is 8. So that is your simplified answer. All right? Look at b. All right, I have u squared v to the negative square over u to the negative 1v third. So I can do this a couple of different ways. If I want to go ahead and get rid of my negative exponents, remember I can just drag them to either the top or the bottom, depending on where they're at. So here, I have v to the second, or v to the negative second. It's at the top, I want to drag it down. So that leaves the u squared at the top, and I'm going to take it down. And then I'm going to take the u to the negative 1, since it's on the bottom, I'm going to take it up to the top. And when I do that, guys, I no longer have negative exponents. Alright, so since I no longer have negative exponents, I'm looking at multiplying u squared times u to the first. Well, when I multiply like bases, I add my exponents. So I have u cubed v to the fifth. Okay? Alright, the last thing we're going to look at in this section is scientific notation, and I realize it's a lot, but this is prerequisite. We should already know this. We're just kind of going through it before we get into the big stuff. Alright, so any positive number can be written in scientific notation. Alright, if you remember, scientific notation is something times 10 to a power. Alright, so let's look at 93 million. I want to write that in scientific notation. Okay, here's the deal. Hopefully you know that that number right here has a decimal. Right now, the decimal is at the end, and we do not show it because there's nothing after that. Alright? So, what I have to look at, and what you have to understand, is I want to rewrite it as something times 10 to some power. Alright. This number right here has to be greater than 0, but less than 10. Alright, I have to be greater than 0, but less than 10. So I'm going to look at this number, and I'm going to figure out where can I move that decimal point that would give me a number that is greater than 0, but less than 10. If I move it here, I'm still way bigger than 10. If I move it here, I'm still way bigger than 10. If I move it here, way bigger than 10. Let's go to the next spot. Way bigger than 10. Bigger than 10. Bigger than 10. I'm getting there because I'm now down to, if I put my decimal here, I'm down to 93. Let's move it one more time. And now I have 9.3. It is greater than 0, but less than 10. Alright, so now I've got to figure out what goes here. Guys, this is a simple count. How many places did you move your decimal? Alright, so let's look. 1, 2, 3, 4, 5, 6, 7. So 9.3 times 10 to the 7th power. Okay. A positive exponent indicates that I am moving the decimal point so I got to look at this a couple of different ways. If I am moving the decimal point to the left here, then it's going to be positive. But if I'm looking at this, and it tells me I have a positive exponent, I'm looking at moving the decimal point to the right. Okay? So, you got to be very careful about how you look at this. Alright, so then let's look at this number. Now, notice this number is really small because it's a 0 point and all these zeros and then a 7. I want to write it in scientific notation. I'm going to do the exact same thing. It's going to be something times 10 to something. Okay? So now let's look at this. I need to know where I'm going to be able to move my decimal. Remember, it has to be greater than 0 but less than 10. Right now, I am nowhere near 0. It is very, very small. So I've got to move my decimal, and I'm going to keep moving my decimal until I figure out where I could get a number that is going to be greater than 0 but less than 10. I have to move it all the way to the end. So I have 7. Once again, it's just a counting matter here. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And this time, it is a negative number. All right, it is a negative exponent. A negative exponent tells me that when I'm in this form, that I am moving my decimal to the left. Okay? All right, so how do you know what to do? Look at your example number 8, converting. Well, it starts out in scientific notation, and it's a positive number, which means I move my decimal point to the right. So I'm going to move that decimal point 8 times to the right. All right, so I have 2.375. I'm going to go 8 times to the right, so 1, 2, 3, 4, 5, 6, 7, 8. Now what do I do with all those empty spaces? I fill them with zeros. So 2.375 times 10 to the 8th power would look like this. 237,500,000. Okay? B is just the opposite because it is a negative exponent. That means I'm going to move my decimal to the left. But in this case, they have given us the actual form of the number. They want us to write it in scientific notation. So because my decimal is here, and I have to move the decimal to the right to get a number bigger than 0 but less than 10, I'm going to have a negative exponent. All right, guys, let's look at this. Go ahead and look at number 10, or page 10. This is the last example we're going to look at. Using that scientific notation, what's the purpose of it? All right, so let's say that I have this. 370,000 times 4,500,000,000 divided by 18,000. Now, that's a crazy number. Think about this. I have to multiply those two. Most of the time, our calculators probably aren't even going to go, I'm not even going to be able to do it on a calculator because the numbers are so big. All right, and then I have to divide it by 18,000. So I can actually use scientific notation to help me. So I'm going to go ahead and look at 370,000. I want to change that to scientific notation. So something times 10 to the something. All right, so I need to figure out, here's my decimal, where can I move it to get to something greater than 0 but less than 10. So I have 3.7 times 10 to the 1, 2, 3, 4, 5, so 10 to the 5th power. Okay? Let's look at 4,500,000,000. 4.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9th power. Alright? And then I can go ahead and also do the bottom. Let's do 18,000. That would be 1.8 times 10 to the 1, 2, 3, 4th power. Alright, so now, some of you may say, oh, that looks a lot better. Some of you may say, I don't like it because it's dealing with exponents. That's okay. Alright, let's look at our next step. We're multiplying here, guys. Alright? We're going to treat this just like when we were talking about exponents. Alright, so I can do 3.7 times 4.5. And then I've got 10 to the 5th times 10 to the 9th over 1.8 times 10 to the 4th. Okay? Alright, so I multiply 3 and 7 tenths times 4 and 5 tenths, and I get 9 and 25 hundredths. Alright, I've got 10 to the 5th times 10 to the 9th. If you remember, because I've got like bases, I can add those. So I've got 10 to the 14th. Okay. Now I can finish this up. I can divide this into 9 and 25 hundredths divided by 1 and 8 tenths. And then I've got 10 to the 14th and 10 to the 4th. Alright, so I would divide 9 and 25 hundredths by 1 and 8 tenths. Alright. And that gives me, wait a minute, I think I messed up here. 3.7 times 4.5. I did. This is 16.65. Alright. Sorry guys, I wrote the wrong number. Alright, so 16.65. Alright, now I'm going to divide that by 1 and 8 tenths, and that's where I get my 9 and 25 hundredths. Alright, divide this. Remember, if I divide, I'm subtracting. So 14 minus 4 is 10. So now I've got 9 and 25 hundredths times 10 to the 10th power. And if I want to, I can write that out. That just means I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be my complete answer. Once again, make sure you check your papers, see what you need to complete for tonight, and then see what you need to complete for tomorrow.